Okay, good afternoon to all. So welcome to this fourth lecture of this third week. And so let me recall that in the previous lecture, what we have discussed, we started discussing about the thing that this polynomial ring with integer coefficients is a unique factorization domain. And in order to do those things, so what we started that, so if you take a polynomial over with integer entries, well, that polynomial you can factor if you think of that polynomial inside Q of x. Then since Q of x is a unique factorization domain, you can always factor this polynomial over Q of x. Yeah. But our aim is to somehow find a unique factorization over ZX itself if f is a polynomial with integer coefficients. And so, for example, if you take this polynomial 6x cubed plus 9x square plus 9x plus 3, and if you write it in terms of, for example, factors, then you can see that 3 occurs as a factor which is lying inside this z of x, and 2x plus 1 and x square plus x plus 1 are the factors. And you can see that so all these factors are irreducible inside zx. And what you can notice that if you would like to factor an integer polynomial, integer polynomial in terms of integer polynomial, then one cannot put the restriction that the irreducible factors should be monic, because then you will not in general will be hoping that you do get such a nice result. Therefore one has to compromise with the monic factors. And so in order to compensate this monicness, and as you can see that if the polynomial coefficients contain certain common divisors, for example 3 is a common factor which lies in this, and 3 is an irreducible element inside z of x as well. Yeah. And so therefore we can take gcd out, and instead of monicness we can put certain we can compensate that monicness with the notion of so-called primitive polynomial. And so here what we see that the definition of primitive polynomial that we have defined, that if an integer polynomial, we will say it is a primitive if all the coefficients do not have any common factor except the units. Yeah. And what we are putting that instead of monicness, what we are putting the condition that leading coefficients an, the highest degree coefficient, should be positive. Yeah. So we are normalizing somehow. Usually in a field we normalize leading coefficient to be 1, but since we are not in the case of field, we are here integers, so therefore the normalization here we are putting as it is a positive thing. Yeah. And and it has certain nice properties, and using the properties of this primitive polynomial, we are going to somehow prove that this polynomial ring with integer coefficients is a unique factorization domain. Yeah. So the very first thing that we need in our discussion is what I will write it as a proposition, that if you take two primitive polynomials, then their product is also a primitive polynomial. Yeah. So let me just write down. So it as a proposition. And so what here we are going to prove that let f comma z be two integer polynomials which are primitive, be primitive polynomials. So primitive polynomials, then their product, then f into z is also primitive, is also primitive. Yeah. So how to prove it? Yeah. So in order to show primitive, what we need to show that if we look at the coefficients of f into g, then they do not have any common factor except the units. Yeah. And so therefore what we need in some sense to prove, so this is the one thing. And well, we need to also check that the leading coefficient of f into g is also positive. Yeah. So these two things we need to check. So if we, for example, if you write h as a notation f into g, then the leading coefficients will be positive. That is obvious because you have given that the leading coefficients of f and g are positive, being primitive. Yeah, so that you can trivial note that leading coefficient of h is positive. Yeah, and in order to show that the coefficients do not share any common factor except the units, what we need to show that if we take any prime number p, prime integer p, then what we need to show that this prime integer somehow should not divide all the coefficients of h. Yeah, so that is, so if we can show this thing, that then what we will get, that they do not have any common factors except the units, of course. Yeah, so aim is to show for a given prime p, for a given prime p, so p does not divide the p does not divide here all the coefficients of h. Yeah, and how to prove this thing? So the problem can be again now translated in terms of the natural homomorphism that you know. I think you know a very natural homomorphism from z of x to the polynomial ring over the finite field fpx. Yeah, here fp, let me just write a better notation instead of fp, z mod pz. Yeah, in this case, so here we have z mod pzx. So we have a natural homomorphism. So if we take, for example, any polynomial inside z of x, then you just go reduction modulo p, the coefficients. If you reduce modulo p, then you can see that will be a polynomial inside this polynomial ring. And so you can also prove that this is a homomorphism. Yeah, yeah, it is a ring homomorphism. Okay, so now, so in order to show that this prime p, given a prime p, what we are going to consider the corresponding this substitution homomorphism going reduction modulo p. And in this language, what we need to show somehow that h bar, if you look at the image of h, yeah, h is an polynomial here. If you look the image, and what we need to show that h bar should not be equal to 0. Yeah, then what we will know that at least some of the coefficients of h is not divisible by p. Yeah, so this is the reduction step. So that is, so therefore it suffices to show that this image of this substitution, if we say let me just write h bar is not equal to 0. Yeah, so by the way, so far it is clear that we somehow we need to show that a given prime p, if we look the image of the polynomial h modulo p, then we need to show that this should not be a zero polynomial. That means if it is not a zero polynomial, that means there exist some coefficients of h which is not divisible by p. Yeah, and now it is, I think, very easy to show that this is not equal to 0, just because, so note that f bar and g bar are not equal to 0. They are not the zero polynomial, just because their coefficients do not have any common factors. So therefore, if you try to look, their coefficients is not divisible by any prime. And so therefore, if you read it modulo p, so they will be non-zero polynomial. Yeah, and since I think it is now obvious, since fpx is an integral domain, what we can now see that if two elements are non-zero, then their product will be non-zero inside an integral domain. This will not have any zero divisor. Yeah, so this implies that f bar z bar, and if you try to see that f bar z bar is actually h bar, because this substitution is a ring homomorphism, so this is not equal to 0, and hence we are done. Yeah, So therefore, this primitiveness has an important property that it is closed under multiplication. Yeah. So this is an important thing that we will be using. And anyway, we have written this as a proposition, but in the literature, it is known as Gauss Lemma. So in the literature, it is known as Gauss Lemma, and but here we are writing it as a proposition, and it is one of the important theorem, I should say, though it is written lemma, in order to prove our results. Yeah. Now, so this is the one thing. So next thing that we would like to discuss, this it is, so let me again write as a lemma, but it is one of the important result. And what we have, that suppose you have a polynomial f of x uh, inside q of x. Well, yes, of course it is, we are always interested in a non-zero polynomial. Then this what, so this polynomial have rational coefficients. And so what this lemma says, that this polynomial, what we can do, that we can clear this, if there is a denominator, if there are certain non-trivial rational numbers, then what we can do, we can clear their denominators, and we can what we can get, we will get some some in rational number, say c, and we will get another polynomial f0x, where f0 is a polynomial with integer coefficients. So here what we will get, that here c is a rational number, and f0 belongs to this polynomial ring with integer coefficients with f0 primitive. Yeah, with f0 primitive. So that means what, that the all the coefficients they will not have any common factors, and the leading coefficient is positive. And so that that is the thing. And moreover, what we can do is that, moreover, this expression, so moreover this expression is unique. This expression, or this, let me just write down, this expression is unique. Yeah. And of course, so let us try to see. The proof is very straightforward. So can anyone of you start proving that how we can write this thing? I have already given the hint. So maybe can I ask some of you that can you prove how we will proceed? For example, this, can some of you, so should I take the name, or you can tell by yourself how should I proceed? Yeah, so can you please tell me what will be the steps? Because fx is given to be your polynomial with rational coefficients, right? So what, so they will have some certain denominators in their coefficients. So what you take, usually you take the LCM of their denominators and multiply with this polynomial f of x. Yeah. And so let us so let us give it as a name. So b times f is equal to f1. Now if you just multiply the LCM of the denominator, so f1 will be an integer. So f1 will lie, f1 is a polynomial with integer coefficients. Yeah. And now what our aim is to do next is that, now since f1 is a polynomial with integer coefficients, you try to look at their GCD of the coefficients. Yeah. And take, if there is some GCD, take that GCD out and look at the leading coefficient of f1. And if suppose a leading coefficient of f1 is negative, I will multiply in the GCD by -1. Yeah. And then that will be so, and if we take that GCD out, then the remaining thing will be equal to some, say for example, a times f0. Yeah, where a belongs to integer and f0 of course belongs to z of x. Now f0 is primitive. F0 is primitive. This is primitive now. Yeah. And so therefore what we see, that if we combine these two things, so what we can see, that f can be written as, say, a by b times f0, and this is our required c, and f0 belongs to this z of x is primitive. Yeah. Now how to prove the uniqueness part? Yeah. So can any one of you sketch how can we prove the uniqueness, that this expression is unique? That means if we take two representation of this f as c times, say, f0x is equal to, say, d times say g0x, if we write in two ways, yeah, then what we need to somehow prove that this c is equal to d and f0 is equal to z0. Yeah, aim is to show that c is equal to d and f0 is equal to z0. Yeah. So how to proceed for this thing? Yeah. Now one thing you can do, you can reduce the problem that c a priori c and d are rationals, but you can reduce your problem to the fact that in fact one can take c and d to be integers. Just you multiply by their LCM of their denominators and make these constants to be integers, yeah, in this expression. Then you can see that these things we can take to be integers. So let us assume, so you can assume that CD belongs to the set of integers, and now you can start how to prove it. Yeah. Now can any one of you, for example, say Shivani or uh, uh, others, can Kishan is there, and then Bharat is there. So can any one of you sketch the proof? How should I proceed? So here, of course, let us try to list f0, for example, is, for example, f0 of x has coefficients, say, a0 plus a1x plus and so on so forth, say an x to the power n. And let us try to write z0 as coefficients b0 plus b1x and so on so forth plus bn x to the power n. Yeah. Then what our aim is to show. So note that, so one thing you can note that they are co-prime, their coefficients GCD, if you try to look a0, a1 and so on, so an, they are co-prime. Yeah, so they have GCD1, and similarly, so what does this imply is that if you just multiply c, c times f of 0 will have GCD c. Yeah, c of a0, c of a1 and so on, c of an, they will have GCD c. Yeah. And now note that we have assumed that c times f0 is equal to d times g0. So therefore this GCD, this whole thing will be exactly equal to, in fact they are equal coefficients wise. That means c of a0 is equal to d of b0. So this will imply that db0, db1 and so on, dbn is equal to d. And here, since coefficients wise they are equal, so therefore their GCD has to be equal. Yeah. Yeah. So but here, so we have written the notation GCD, and well, we have not defined the GCD precisely. So here a priori it seems that c is equal to d, but here there is an ambiguity. We have not defined whether for us GCD, I mean positive or negative, that we have not defined. So they are actually equal up to units. That means c is equal to plus minus d. Yeah. So one may take GCD to be, for example, minus C here. One may say that I will take GCD here to be plus D. Yeah. So now we have to somehow eliminate this ambiguity to prove that C is equal to D. Yeah. Then how to prove it? Yeah. And how to, so first of all, it is very clear if C is equal to plus minus D. So what we can see that from this expression, that f0 will be equal to plus minus times z0. So this implies that the polynomial f0 will be maybe up to units they are same. z0. Yeah. Now what we need to eliminate the ambiguity coming from the units. Yeah. And how to eliminate that ambiguity. So any one of you can say how to eliminate this ambiguity. What we would like to say that f0 is precisely equal to plus times g0.
F0 and G0 has positive of
Yes, right.
positive
Yeah.
coefficient,
So
positive
they,
leading term.
yeah. So since f0 and z0 both are primitive, so by the very definition of primitiveness, the leading coefficient of both of them are positive, and so they has to be same. F0 is equal to z0. Otherwise, one will have positive coefficient and the other will have negative coefficients. Yeah. So this implies that f0 is equal to z0 since f0 and z0 have positive leading coefficient. Yeah. And if what we have seen that if f0 is equal to z0, and therefore this implies in fact that the ambiguity coming in the sign of c and d are also clear, that c has to be equal to d. So this is a very straightforward what should say lemma, and as you can see that it is very clear the way we clear the denominators when we do fractions or addition of fractions. It is very similar to that, and we will see the power of this lemma, that how this particular lemma is helpful to deduce certain nice results in the case of polynomial rings over integer coefficient. And one thing I would like to just say that here we are focusing only for polynomial ring z of x. So let me just say, but the arguments that we are floating in proving all these results over z of x will be actually applicable for any unique factorization domain. And since we are in the case of integral domain, instead of q, one can replace the field of fraction of that unique factorization domain and so on. The only thing that may bother any one of you is about this thing, that the notion of primitive polynomial. Here we have defined that may bother, but here only thing, since for example here we are normalizing an to be positive, there what we can say that they are the units, they that leading coefficients we have to somehow compromise with the units, and there will be ambiguity up to units. Yeah. So up to that, and everywhere you will replace plus minus 1 by units, but then the same argument will actually be proving that in fact if you take any unique factorization domain, and if you look a polynomial ring over a unique factorization domain, then that will be again a unique factorization domain. Polynomial ring over a unique factorization domain is a unique factorization domain. Okay, so this is the thing. So let me just write down certain remarks that is clear from this thing. So this is about very clear that if we take a rational polynomial, then we have this. Suppose if your polynomial itself,
Excuse me, sir.
yes, yeah.
Sir, what can we say about over z iota, where the leading term will be like positive always, or we can consider some polynomial whose leading term may be iota
Where?
in z iota set of Gaussian integers.
Uh-huh.
Hmm.
Oh, so
So
you are
primitive domain.
talking in Jedi, right?
Right.
Okay. Okay, there
So
that
there
leading
the primitive term.
coefficients, yeah, leading coefficient. So for example, there also what you can do that you have 4 units in Jedi. That is again not a big
Right.
problem. There you can up to units, if you try to normalize, you can again do that thing. That should not create a problem. But in general, if you have many units, so there what you may not be able to properly normalize. For example, even positiveness, notion of positiveness, for example, may not be there in any unique factorization domain. Yeah. So for example, if you are in the case of real numbers, you have the notion of positiveness. Even if you go even in the complex numbers which are real, you know that there is a notion of you can distinguish up to this positive and negative, and of course pure for example, complex field is not an ordered field. In general, their positiveness is not there, but wherever you can see that as a subfield of say complex numbers, you can adjust with this notion. I think this argument will go through. But for example, in general integral domains, for example, there is you are not able to distinguish the signs. Yeah. Means if you have a general integral
Okay.
domain, so as far as if you are in the case of reals, it's okay, or subfields of real. But in general integral domains, what is the meaning of sign? Yeah, so there one might have a problem to normalize the leading coefficients, and then one need to deal that definition
Okay,
up
sir.
to units in general. Yeah.
So Z root 2, we can may bother where they have a lot of units, like infinite
Yeah,
number
Z
of
root
units.
2 have a lot. In fact, I think it has infinitely many units. So there everywhere one need to I think prove the results up to units. Yeah. So that means what one can
Okay.
say, that leading coefficients an, if you take for example true primitive polynomial in that sense, then the leading coefficients only differ by a unit. Yeah, so therefore here we are trying to say that C is equal to D. Then in that case you might be able to say that C is equal to D up to units, and F0
Okay, sir.
is equal to Z0 up to units, like this.
Okay, sir.
Yeah.
Thank you, sir.
Yeah, in general, like that one can say for any unique factorization domain. Okay, so far any more questions or any other doubts, so we can discuss. And so if you have, please let me know, and then we can proceed further.
No question.
Okay, good. So let me just it is a simple remark that so if you take integer polynomial, so for example, if your polynomial itself has integer coefficients. Yeah, so what we say that so if we write f as say C times f0, so what here C will be, and it is very obvious that if we have integer coefficient, so C will corresponds to the GCD of the coefficients with the sign of the leading coefficients. Yeah, C takes care of the sign of leading coefficient, and it is a GCD. So here C we will put plus or minus GCD depending upon the leading coefficient of F0. Yeah. So that I think is clear, and I will leave it to you to write down precisely what is this C and all, but it is, I just told it is like that. Yeah. And well, so it is, and well, if you would like to and let me also, so this is the thing. And the second thing, that C in the above lemma is known as the content of let's say polynomial f. Yeah. So this is the thing. So C in the above lemma is known as content of f. Yeah. So this is the just a terminology. And well, so let us try to see certain applications of these two Gauss lemma and this particular lemma. So we will be referring this lemma as simply lemma, and wherever we are using Gauss lemma, we will write it as a Gauss lemma. Yeah. So let us start certain important results in this direction. And so again we will write that thing as a proposition, and then we will proceed further. Yeah, so here what is the first result that we are going to quote is for example, if you take polynomial, so if you take a primitive polynomial, so if f is a primitive polynomial in ZX, here f primitive, and suppose if you have z belongs to ZX, be any polynomial, be any polynomial. Yeah, now what we have given, suppose that this primitive polynomial f divides g in q of x. Yeah, so this divisibility in this polynomial ring q of x, then well, since both are the integer coefficients, and we have given that this divisibility inside q of x, but as our intuition says that in fact this divisibility should be inside z of x also. Yeah, and in fact it is the conclusion of this proposition that so here, so what is the meaning of, so let me just write down f divides g in q of x. That means you can write this g as f times q. F times q is equal to g, where q lies inside q of x. Yeah, so this is the thing we have given. Then what does this theorem says, our proposition says that then in fact this divisibility is in fact inside z of x, then q of x lies inside z of x. Yeah, and hence f divides g in z of x. Yeah, so this is the proposition, and what does it says that, so let me just write this first part, that if you have a primitive polynomial and if you have another polynomial with integer coefficient, and if you know that the divisibility is there inside q of x, then this proposition actually says that in fact this divisibility is inside z of x also. Yeah, and the second part is again a consequence of the first part, but let's write it down, that if you have, say for example, two polynomials f and g inside, say, z of x. Yeah, so if you have two polynomial f and g inside z of x, now if they have a so if they have a common if they have, so let me just, if they have a common non-constant factor, common, say, non-constant factor in q of x, in say q of x, then they have a then they have, then let me just write, they have a common non-constant factor, non-constant factor in z of x also, z of x as well. So this these are the two things that we are going to see now. The proof, can you sketch me the proof? And I can give you the hint that we need to use this the above lemma as well as Gauss lemma to prove A. So can you start proving or giving hint how to start that one? So what we need to show that this q is an integer polynomial, which we know a priori as q is a rational polynomial here, but our aim is to somehow, if we can show that q is an integer polynomial, then we have proven this the part A of this theorem proposition. Yeah, okay, so our aim is to use lemma as well as this Gauss lemma, and how to use these two things. So since of course we have given that q of x belongs to this q of x, then we can use the above lemma to write it in terms of primitive polynomial. Yeah, so what you can say that by the above lemma, what you can prove that this q of x is equal to some constant times q node x, where q node is an integer polynomial which is primitive, yeah, and C is of course say a priori it is a rational number, yeah. And now our aim is to show that actually C is equal to, say, C is an integer, then we are done. Then Q of X will be an integer polynomial, right? Yeah. Now can you use now Gauss lemma to say something? So in order to use Gauss lemma, one need to have at least two uh, 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 two primitive polynomials, yeah, so that one can apply the Gauss lemma to say that their product is primitive. And in order to do that, we have given that since f divides g, yeah, in Q of X, yeah, that means what? And f is given to be primitive, yeah, by the very hypothesis. And therefore, if we write g as, say, f times q, yeah, and then and q we have already written in terms of this thing, so this is same thing as c f times q0. Now this thing will be primitive, yeah, this is primitive, yeah, primitive, this is by Gauss lemma, yeah. So product of primitive polynomial is primitive. And now if you one would like to write g also as by using the above lemma as in terms of primitive polynomial, then what we know that if one writes g as, say, some constant times, say, some constant times z0, and since this expression is unique, so this c should be equal to this c, so that's one thing. And z0 is an integer polynomial, yeah. So and here what we know that, and z0 belongs to z of x, yeah, with g0 primitive. Yes. Now now what our aim is to say that uh, uh, that our aim is to somehow say that c is an integer. So can you now guess how one can say that c is an integer? That's very obvious from this thing. So this implies that c belongs to z. Now can you tell me why? Please.
G is in zx.
Right, yeah. So since g is an integer polynomial, yeah, and so therefore whatever, if you write it as c times g0, then the content has to be integer, yeah. So therefore that's done. So therefore here this argument one can write as, since z belongs to z of x, yeah, and so therefore we have shown that c is an integer and therefore q of x is an integer polynomial, yeah. Q of x is an integer polynomial, and so we are done, yeah. So this is the first part. Now can any one of you start proving the part B of this thing? So B part. So what is in this B part? That we have given that we have given two integer polynomials, and suppose if we know that they share a common factor inside Q of x, then what we need to show that they share in fact a common factor inside z of x. And I think that is again an application of part A. So can you sketch the proof? So for example, suppose this thing, suppose you have a common factor, say h divides f and h divides g in Q of x. Yeah, this is the meaning of they have a common factor in Q of x, yeah. Now here so h belongs to Q of x. Well, now again we can use the above lemma to write h as some constant times h0, right, where c belongs to q, yeah, and h0 belongs to z of x, right? Now if h divides f, then h0 will also divides f and g, yeah. So this implies that h0 divides f and h0 divides g in q of x. Is it clear, or you have any doubts? Because h0 divides, say, h, and and h divides f, so you can write this thing in q of x. But our aim is to find a common factor inside z of x. And we can use part A of the above proposition, and what the part A has condition that if you have a primitive polynomial and if we have an integer polynomial and suppose the divisibility happens in q of x, then it is in fact in z of x, yeah. And so we have given h0 is a primitive here, yeah, because by the very writing this thing, so here h0 here is primitive, yeah. So, and f and g are integer polynomial, that is by the hypothesis here. And so what we see that the hypothesis of part A of the proposition is true. Yes. So hypothesis of the part A of the proposition is true. Then what we can say that, so this implies that h0 divides f and h0 divides g in z of f. Yeah, so, and this is just because by part A of proposition, yeah, by part A of the proposition. And so therefore what we see that f and g have a common factor in zx also, yeah. So okay, so do you have any doubts or comments? Okay, if there is no doubts or comments, so let us try to write an important corollary out of this proposition. And what this says that if so suppose if you have given a non-constant polynomial fx, say, belongs to say z of x, yeah, and say it is non-constant, fx is not constant polynomial. And suppose if you know that if f of x is irreducible in z of x, then can we say that this polynomial so if you so some polynomial, for example, if you have a polynomial in a smaller ring, if it is irreducible, can we say that is still irreducible in a bigger ring? So in general, I hope this is not true, yeah, that if you have polynomial in a smaller ring, then this polynomial if it is irreducible in the smaller ring, then it is irreducible in bigger ring may not be true always, yeah. But if you are in a nice rings like unique factorization domains, and if you know that if a polynomial is irreducible over a unique factorization domain, then you can say that polynomial will still be irreducible over its field of fraction, then fx is irreducible in q of x. So this is a corollary of this above proposition. Can anyone of you prove it? So now try to suppose not. So how to prove this is, so suppose f is not irreducible, suppose f is reducible in q of x, then we need to get some contradiction to the fact that fx is irreducible in z of x. Yeah, that means you can write f as say g times h in q of x. Well, yeah, now since g and h are in, so g h belongs to q of x, yeah. Now what we can do, we can write g as some constant times g0, right, where z0 belongs to z of x primitive, yeah, primitive, yes. And then what we can see that z0 divides f in q of x. Yes, and as you can see that g0 is a primitive polynomial and f is an integer coefficient polynomial, and this divisibility happens inside q of x. Then by part A of our proposition, what we can say that this implies that g0 divides f in z of x. Yes, and similarly you can also prove that h0, if you look the primitive polynomial associated with the factor h, then you can prove that h0 divides f in z of x. Yeah, and so this implies that f has a non-trivial factor in z of x, has a non-trivial factor in z of x. Yes, which is a contradiction to the fact that f is irreducible in z of x, which is a contradiction. Yeah, and so therefore what we see that if you have polynomial over integer coefficient which is irreducible, then it is still irreducible over its polynomial. If you look z, then you can very well say that if you look at the field of fraction and corresponding, if you look the polynomial ring, then this polynomial is still irreducible. Okay, so we will be using these things to prove our result that ZX is a unique factorization domain. And in order to prove ZX is a unique factorization domain, what our aim is to do, so let me just, so far what we have done and what we have to do, so let me just sketch it. And so what, so in order to prove UFD, and if you remember a result that we have proven that in order to prove UFD, what we need to show that existence of factorization. So existence of factorization plus irreducible element is a prime. So yeah, so now so far if we try to see what we have done so far work by using this, we can prove the existence of factorization. And now our aim is to somehow show that every irreducible element is a prime. Now let us first try to see that how we can deduce that existence of factorization in Z of x. Yeah, so far, so let me just, so suppose you have polynomial with integer coefficients, and what we would like to say that, well, existence of factorization is there inside Z of x for any polynomial. And well, for in order to do that, what we can think of this polynomial. So for example, if this polynomial has certain GCD, then what we can do that we can write f as some constant times f0. Yes, where c is an integer. Now this integer can be written as a product of prime numbers. So this has a nice factorization, and that prime elements are again irreducible element inside Z of x. That one can check, and maybe it is we are going to prove that part. Now how to factor f0x inside Z of x? So f0x belongs to Z of x. Well, it is primitive. Yeah, primitive. Now what you do that you think this polynomial inside q of x. Yeah, you think this polynomial inside q of x, and q of x has a unique it is a unique factorization domain. We can factor it f0x in terms of say f1, f2, and so on. Yeah, fn x. Yeah, here and we are now what we are going to say that f0 is an integer coefficient polynomial, and which is a primitive polynomial. And what our aim is to show that we can use this property. We can use part B of this theorem. And what does this says the part B of this theorem, that if you have a common factor in Q of x, then you do have a common factor in Z of x also. Yeah. And so therefore, if we use that fact, then what we can say that we can write a common factor, we can find the common factor of f0 inside z of x also. And therefore we can using these things, we can say that existence of factorization holds inside z of x, and only thing that we need to prove that every irreducible element is a prime. So are there any doubts or any comments?
No, sir.
Yeah, so you can, in fact, you can use in order to prove that suppose f0 is a primitive polynomial here, and if you write in terms of factors here, and what we have shown in this argument, if you try to mimic here, you write this factorization, f is integer polynomial, you write this factorization in q of x, then what we shown that corresponding primitive polynomials are the factors of f. Yeah, g0 and h0. Yeah, and so therefore you do get a factorization. Yeah, and inside z of x, and the only thing that we need to ensure that every element, every irreducible element of z of x is in fact a prime element. And so therefore now our aim is to classify what are all the irreducible elements inside z of x. That means whether every irreducible element is a prime or not. Yeah. So let us try to proceed further. And so this is again as a theorem that we are going to discuss. So let me just write down this as a proposition here. And what this says that, so let f belongs to z of x. Yes. Say integer polynomial, and f belongs to zx with, say, positive leading coefficients. So we will start with positive leading coefficients. And we would like to say something about primitiveness, so that we can write, so that we will have beforehand the requirements that we need in primitiveness. Then f is irreducible in z of x, in z of x, if and only if, so if and only if either so either f is a so irreducible elements in z of x will be of two type. For example, if you take a prime integer also is an element here, and what we are going to say that prime elements are also irreducible elements inside z of x. So f, no, this irreducible, so the what will be the irreducible elements, one thing will be that f is a prime integer, so either f will be a prime integer or it will be irreducible primitive polynomial. F is primitive polynomial, yeah, which is, of course, which is irreducible in q of x. Yeah. So in the second part, what we need to prove is only primitiveness, because this irreducibility then follow by the above corollary. Yeah. So irreducibility will follow from this corollary, that if you already have irreducible polynomial in z of x, then it will be irreducible in q of x. So therefore, what we see that if you have an irreducible element inside z of x, then it will be either prime integer. So this f may be a prime integer, and otherwise it will be a irreducible polynomial which is primitive. And this primitiveness is also very natural, just because if f is irreducible, that means there is no non-trivial common factor among their coefficients. Yeah, because if there is some non-trivial common factor among their coefficient, for example, say 2 or 3, then what we see that we have written f as product of two irreducible elements non-trivially. So therefore, in order to say that there is no non-trivial common factor, actually that takes care of the word primitive. Okay, so let us try to prove it. And so what we need to, so let us first start with this direct part. That means suppose f is irreducible, suppose f belongs to z of x is irreducible, then what we need to prove that this f is a prime integer, either f is a prime integer or f is a primitive polynomial. Yeah, so what we can do, that we can write this thing, that f has some constant times f of 0 by the above lemma that we have put it. Yeah, and here what we see, that f0 of course is a primitive, f0 is primitive. Yeah, now what we have given, that f is irreducible, and so therefore what we see, so this implies that, so f cannot have a non-trivial proper factors. So this implies that either c is equal to 1 or f0 is equal to 1. Yeah, so now let us try to see what will happen, that if f0 is equal to 1, then what we can say, that this implies that f is a constant, this implies f is constant. Yeah, and that will be exactly equal to c. And and f is constant and irreducible, and so this implies that f is a prime integer. Yeah, f is a prime integer. So any constant and irreducible elements inside z of x are prime integers, that we know. So this is the thing. And now the second thing, that if c is equal to 1, if c is equal to 1, this implies what? This implies f is equal to f0. Yeah, and of course f0 is primitive. Yeah, that is obvious, because by the very factorization we have f0 is primitive. And so therefore what we see, that f0 is a primitive polynomial, and and f is irreducible in q of x by the above corollary. Yeah, and this is by the above corollary. Yeah, so therefore what we have proven, this direct part, and this converse part is again obvious, because we know that uh, if f is a prime integer, or f is a primitive polynomial which is irreducible in q of x, then of course it will be irreducible in z of x. Yeah, so this is obvious, that you can prove by yourself. And so therefore this theorem, this proposition actually classifies or says what are the irreducible elements inside z of x. Yeah, now so therefore now next proposition is still our aim is to prove that every irreducible element in z of x is a prime, is prime. Yeah, and so let me just sketch the proof of this result, that how to prove this thing is a, so f, if you take f belongs to z of x irreducible, yeah, then there are two cases, either f is a prime or a prime integer, or f is a primitive polynomial. Yeah, so let us try to deal with the two cases, and our aim is to prove that this irreducible element is a prime. So that means what? To show f is prime, what we need to show f is prime, what we need, that is f divides say g of h implies f divides g or f divides h, that we need to show. And so for example, if you look at the case first, that f is a prime integer, so suppose f is equal to p is a prime integer, then what we can do, that since f divides g, we can write this g as what we can write g as c times say c0, where g0 is primitive, let's say, yeah, c times g0 where g0 is primitive. And also we can write h also as say d times h0. So h we can write, for example, d times h0, where h0 is also primitive. And what we can assume that this G0 and H0 are primitive, and therefore by using this Gauss lemma we can say that this G0 and G0 times H0 is primitive. Yeah. So therefore what we see that uh, 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 the coefficients of G0 H0 doesn't share any common factors, and so therefore this prime integer p will not divide some of the coefficients. So p doesn't divide some some coefficient of G0 H0, and let's say it is equal to a, say some coefficient of this is say a, which p doesn't divide. Otherwise if it divides all the coefficient, then they have GCD, which contradicts to the fact that they are primitive. Yeah, but what we know that this p divides this f divides g times h here. F divides g times h, therefore p divides g times h, and so therefore p divides this cd times a. Yeah, cd times a, because p divides g of h, that means p divides the coefficients corresponding to that, and so therefore what we see that p divides cd. Yeah, because since p doesn't divides a, and so therefore cd are integers here that we can see. So therefore what we can see that either p divides c or p divides d, since p is a prime integer. Yeah, so this divisibility inside this integer, so therefore we can conclude that p divides c or p divides d is a prime integer. Yeah, so this is the first part, and the second part what we need to say that if f is a primitive polynomial. So let me just quickly case 2 also. So if f is primitive given, then what we can say that which is of course irreducible in q of x. F is primitive which is by the which is irreducible in q of x. Then what we can say that since q of x is a PID, and we know that inside a PID every irreducible element is a prime element. So therefore what we can say that f is prime in q of x, inside q of x, and therefore what our aim is to show that f is a prime inside z of x also. Yeah, and now I think you can prove now that if f divides gh, f divides gh, so this implies f divides g or f divides h in q of x. That is by the very fact that f is a prime element. And now you use the fact that f is a primitive element and g and h are integer coefficient, and this divisibility happens in q of x. Therefore by the part A of proposition we can say that by part A of proposition what we can say that this implies f divides g or f divides h in z of x as well. Yeah, and so therefore f is a prime element inside z of x, and so therefore what we are able to prove that every every irreducible element inside z of x is a prime element, and hence z of x is a unique factorization domain. And so I would like to stop here. So thank you very much. So sorry, I think 5 minutes ahead. So sorry for this. And so